If you didn't understand what that meant, don't worry about it. Our measurement can still be the same. It can just be position only. And you might ask, well, if it's just position, how do you ever get velocity and acceleration? These equations that we'll set up will, when you sort of do the invert to solve for things, it figures out that you have to take the differences between positions divided by delta time as velocity and the difference between velocities divided by delta time for acceleration, even if we're only measuring position. So it's time to introduce the Kalman filter. The Kalman filter is a method of tracking linear dynamical systems with Gaussian noise. And what's really cool is both the predicted states and the corrected states are Gaussians, right? So you're only maintaining the mean and the covariance of your state in order to run your filter. And also the calculations are very straightforward. I'm not even going to derive the equations here. We will get some intuitions, but you can show that it's a relatively straightforward manipulation of these linear matrices. So in pictures, the Kalman filter can be described as the following. All right, you start off in the blue here is at the top left. That's your prior belief, right? So let's suppose we have some density. Now, what kind of shape is it? It's a Gaussian. Why? Because this is a Kalman filter. Okay, Kalman filters are built on Gaussians. You want to have a non-Gaussian? Too bad. This is a Kalman filter. Things are Gaussians. We'll do some other little stuff later. For now, everything's. So the first thing that happens is, in this picture, is referred to as a deterministic shift. Remember when we multiply it by that linear system? So basically, that's the part that you know what happens. And that's shown here in green, where the Gaussian bump has just slid over to the right. So if I'm a Gaussian bump, which I've been accused of on a variety of times, the first thing that happens is I slide over to my right. That would be your left. Now, Megan is wondering, should I move the camera? I don't know what this guy's going to do. I'm going to come back in a minute. All right. Anyway, so the first thing we do is we slide. And we know that's the deterministic part. Then comes the part that's referred to in this picture, and I left it in here because I think it's a cool way of thinking about it, stochastic diffusion. But it's basically the addition of noise. And this is referred to the process noise. So now we've done two things. We've deterministically stepped one way, and we've grown a little fatter. Both problems. Anyway, the idea is when I'm taking a step forward in time, I use the part that I know. I think I was moving, 3 meters per second, and it's a second later, so I think I've moved 3. But I also know that I'm not perfect in my knowledge. Right? That's never my problem. That's somebody else. But no. Anyway, I know I'm not perfect in my knowledge. So therefore, over here, my variance is wider. Okay, so I've now expanded my uncertainty. Then what happens is I take a measurement, and that's shown here as Z. Okay, so I take some measurement, and what happens is if you take a look at the density in the blue here, you'll notice that it has shifted back a little bit based upon the Z, and it has also gotten narrower. Okay? It's very important to think about this in the Kalman sense, and we're going to do more of this in a minute, right? We shift, expand, measure, shrink. Okay? Actually, shift, expand, measure, correct, shrink. That shrinkage happens because whenever you take a measurement, you're getting new information. New information can only reduce your uncertainty. That's going to come back in a minute to be a little strange. I want to introduce, we're going to keep doing this Kalman filter now on the 1D state, and I want to introduce a little bit of nomenclature, some a way of writing things down. So what we have here is we have this inner loop that we talked about, where we predict, make a measurement correct, and then time advances. Okay? So time advances, we predict, we make a measurement, we correct. The first thing I want to show is, in our prediction, which is probability of xt given the measurements up through t minus 1, our prediction in Kalman land here is going to be modeled, written as mu minus sigma minus, or sigma squared minus, right? This is, and see, of time t. So mu minus sub t, sigma squared or sigma minus sub t, that's the prediction of the mean and the covariance before I take the measurement at time t. That's why it's referred to as minus. Then I take my measurement, all right, and my corrected version, which is now the distribution of x given the new measurement y sub t, is referred to as mu plus sub t, sigma squared or sigma plus sub t. So I have these two things. I have mu minus, sigma minus at time t, that's the prediction before the measurement, mu plus, sigma plus at time t, that's my correction after I've taken my measurement. Let's go through the prediction and correction just a little bit in the Kalman 1D case. Remember, we're going to assume that the state at time t, okay, is just a constant times whatever the state was at t minus 1 plus some noise that's added, some process noise, right? So the first thing we would like to do is we would like to know our estimate. What's our best guess at time t given everything t minus 1 when we've got this Gaussian model? Well, we're going to write this the following, right? If something is a Gaussian and I multiply it by a constant, what does that become? It becomes another Gaussian. Or another way of saying it, I have some variable that's distributed by a Gaussian, and I multiply that variable by a constant, I get a new value out, but it's also a Gaussian, right? And in fact, if you remember from probability, right, its mean is just going to be that constant times the previous mean. So that's what this equation here says. This equation says that if I have my belief about the mean at time t minus 1 after I've done all my work at t minus 1, and if I believe that my dynamics are multiplying the state at every time step by d, my belief before I take a measurement about what the new mean is just going to be d times that. That's what this equation at the bottom says here, right? Mu minus at time t, the predicted mean, is just d times the mean from what I had before, okay? Because d is my multiplier. All right, so you remember that when I multiply something by a constant and it's Gaussian, the mean just multiplies. But what about the variance, okay? So now we have to update the variance. There are two things that are going on. First of all, we're taking some previous variable and we're multiplying it by a constant. That variable had some sigma squared to it. And maybe you remember, if you have a Gaussian, when you multiply that by a constant, its variance goes up by the square of that constant. So just in the multiplication part, all right, whatever the variance was before is going to go up by now d squared. But wait, we're not done. We also added in some more noise when we took that step, right, of d squared. So that means the new variance before we take a measurement is made up of two components. It's d squared times whatever the variance was before, so that's written as d sigma t minus 1 plus squared. Sigma t minus 1 plus is the standard deviation. If it's squared, it's the variance of what we had at the end of t minus 1. We're multiplying everything by d, so we multiply that variance by d squared. That's what this term over here is. And then we added in some more noise because of uncertainty of how the thing actually then moved. That is this d squared, okay? So even if we were multiplying by a 1, that is, even if we had no idea, there was, you know, everything was just a 1, our variance would still grow because of the added uncertainty, all right? So the update of the mean and the update of the variance for the Kalman is written like this, all right? What about the correction, okay? Well, the correction is a little complicated, so what I'm going to do is I'm going to show you the formula for it, then I'm going to give you the intuition behind it, then I'll show you, actually not the formula, I'm going to show you the simple formula for the 1D case, give you the intuition behind that, and then give you the full formula for the ND case. First, remember that we're assuming our measurements are, again, just some constant times the actual state plus some Gaussian noise. Okay? That's our linear system plus Gaussian noise for the Kalman filter. Remember, we have our predicted state. We just did that. We said that that's mu sub t minus, right? That's the predicted mean. And then sigma t minus squared, that's the variance of the prediction. And what we want is we want the corrected estimated distribution. That's what this is here, all right? So in Kalman, with linear Gaussian dynamics and Gaussian measurements, the corrected distribution is defined to be, and I'll show you that, a new Gaussian, okay, which is now mu t plus and sigma t squared plus, all right? And what I want to do is I want to show you the formula for that and then give you the intuition behind it, okay? This is the formula for the mean, okay, so here is mu t plus, and it's a combination of mu t and the y, which we'll get to in just a minute. The update of the variance is here, so sigma t plus squared, okay? And you'll notice that what's happening is that this number, if you just do a little bit of this math here, is actually going to end up being smaller, okay, than the predicted variance. And that makes sense. Why? Because remember, after we take a measurement, our variance goes down. So let's take a look at the mean. This one will be a little bit more clear, all right? So this is the equation just copied from the previous slide to this slide, all right, for mu plus. Step with me. I'm going to divide by m squared, okay? So when I divide by m squared, okay, so you see I've just divided by m squared, so there's an m squared down here, and this m becomes m there, and this becomes an m squared there. Okay? Cool. So what is that?
I have no idea.
Well, yes, you do. Here it is. Look, see this yt over m? Remember, y, the measurement, was just m times x. So yt over m, that's the measurement's guess of what x is. Right? If you were looking just at the measurement, that's its guess. Now, mu t minus, what's that? What mu t minus is, that was our prediction, right? That's the mean. That's our best guess as to what x actually is at time t. Okay? So we've got these two things in here, right? We've got mu t, which is our prediction, and y over m, which is our measurement's guess. We have to somehow combine them. Well, how do we combine them? Well, what's this value, right? This is just sigma squared divided by m squared. That is the measurement's variance divided by m squared. That's the variance if you were to compute x just from the measurement. So this guy right here, that's the x computed just from the measurement. The variance of that is sigma squared m over m squared, because y was just mx. All right? So that quantity right there, circled in blue, that's the variance of x computed from the measurement. And what is the last term there? Sigma t minus squared, that's the variance of the prediction. And you might say, well, so what?
So what?
What do you mean, so what? No. What this means is that the entire mu t plus is just the average. It's a weighted average of the prediction and the best guess based upon the measurement. And so down here in the denominator, that's just the sum of the weights. It is just a weighted average of the prediction plus what the measurement is telling you, which of course is what, in some sense, the universe has to be, right? The whole idea is you're making a prediction, you're getting a measurement. Both of these are sources of information, and you want to integrate them. In fact, we can take a look at that a little more carefully, all right? So here are the expressions that we have before for the new mean and the new covariance. Suppose there's no uncertainty prediction. What that means is that sigma t minus equals 0. I don't know how that would have happened, but let's suppose you just know where this thing is. So then what happens is if this is 0, okay, gee, let's take a look over here. Then this thing is 0 here, this thing is 0 here, this thing cancels out. What it means is that your best update is the one that just uses the prediction, because you knew exactly where it was going to go. And furthermore, your new covariance is 0. That is, you have no uncertainty. Another way of saying this is your measurement is ignored. Okay, so if I'm sure of my prediction, I should ignore my measurement. Likewise, what if there's no measurement uncertainty? Suppose your measurement's perfect. What should you do? Well, if you plug sigma m equal to 0 in here, you'll see that mu t plus, your new best guess, is just the measurement divided by m. That is, it's just the measurement's guess as to what x is. You're totally ignoring the prediction. And this is what Kalman does for you, right? It gives you this trade-off between how much you pay attention to the prediction versus how much you pay attention to the measurement as a function of the uncertainty of the prediction and the uncertainty of the measurement. And that's what makes it so powerful. All right, now I'm going to make some simple changes with A and B, right? So A is here, and A is just this quantity there, and B is here, and B is just this quantity there, in which case this whole expression, I replace the A and B, keep going.